So now we have described the algorithm MergeSort, and again we illustrated it on this list where we took the list, we kept dividing it until we got to the leaves. For each one of them, there is nothing to do; they are already sorted. We go up and do the merge. When I began describing the algorithm, or before we start describing the algorithm, I said we are gonna go into an O of n log n algorithm. So what is the efficiency? Or why does the efficiency of this algorithm? Why is the time complexity of this algorithm O of n log n? So this is where we need now to analyze this. Now, this algorithm, notice that this algorithm is different from algorithms we have seen so far. This algorithm is a recursive algorithm. I say I want to sort this list. I don't know how to do that. I'm going to divide it into two sublists, and I'm going to sort them. So notice that to sort the big list, divide it into two halves, and then sort the halves. But I'm using the same term again. I'm saying to sort these, to sort this big list, sort the two halves. But this is not really sorting because I just invoked the same word again or the same function again. And to sort this, sort the two halves. And sort each one of them, sort the two halves. So this is what we call a recursion here, right? I'm calling the function multiple times, but every time I'm calling the function, I'm calling it on a smaller instance of the problem here. So I called MergeSort on this list, then it will do MergeSort on this, MergeSort on this. MergeSort on this is going to do MergeSort on these two, in each one of these. MergeSort on this is going to do MergeSort on each one of them. So this function, MergeSort, is going to be called once on this, is going to be called once on this, once on this. It's going to be called here, 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 here. It's going to be called again on each one of these. So it's going to be called many times. At the end, when it is called here, when I say MergeSort of this list, it will look at the list, say, okay, it has one item, done. It is sorted. And then after that, the merge comes into the picture and starts doing the merging. So no more sorting now, it's just merging them, right? So what is the running time? And here, since this is a recursive algorithm, we do the technique for analyzing the running time of such an algorithm is a bit different now, right? So I am doing, let's look at it, is that when we are doing MergeSort of a list of n items, let's say, for example, it has n items from position 0 to n minus 1. What MergeSort is going to be doing, it is going to be doing three things. It's going to be doing MergeSort on L and the first half. Okay. And then it's going to be doing MergeSort on L, the second half, which is n minus 1. And then it's going to be doing the merge of these two. Once I'm calling MergeSort on this, I get it sorted. I get MergeSort on this, I get it sorted, I will do merge. So if I look at this, once this is sorted, I'm doing merge. Okay? So I'm doing MergeSort on a list of size n. To get this, I'm doing a MergeSort on a list of size n over 2, MergeSort in a list of size n over 2, and I'm going to do merge the two. How long does merge take? Suppose I have two lists. This is of size n over 2, and this is of size n over 2. Remember, these were A, B, and I copied them into C, which is of size n. Right? The merge is going to look at these two items first, compare them, and copy the smaller, then the second, and copy it, and so on. This list is going to have n items. Okay? When we began, it was empty. When the merge ended, it was n items in it. So there were n items copied here, so we know it does at least O of n amount of work. And in fact, it does O of n amount of work, because for each item, I'm doing just one comparison here. Right? So for each element here, I'm doing a constant amount of work. So merge of these two lists into this is going to take O of n. Okay? So I know that this merge is going to take O of n amount of work. The question is, how long does the entire function take? So suppose I'm trying to get at the running time of MergeSort, which is T of n. This is a function that is the number of steps that MergeSort will take on a list of size n. So what is T of n? T of n equals what? Right? I know T of n equals O of n. for the merge plus something, because we are doing the merge, but we are doing also two other things, right? So it's O of n for merging the two halves. But how long does it take to do merge sort and to do merge sort? For a recursive algorithm, probably your first impression was, okay, let's repeat the same exercise and say, okay, now how long does it take this, and then how long does it take this, and keep repeating this exercise and adding these kind of terms. But for a recursive algorithm, there's a much simpler technique and a much more elegant technique for analyzing this, which is, I know that the running time of merge sort is T of n. I don't know what T of n is yet, but I know it is T of n. I'm calling it T of n. Now, if this is T of n, it takes T of n to do merge sort of a list of size n. This is the same function, exactly the same function, not modified at all, but applied to a list that is half the original size. So this is the same function like this, but applied to a different instance of the problem. This was applied to the big list. This is applied to half. So if this takes T of n, this is going to take T of n over 2. This is T of n over 2. And this is the same story, T of n over 2. So what we get from here is that we have 2 T of n over 2. This is the running time of merge sort. Now, when I write something like this is probably the first time you have seen something like this, and it doesn't look like anything we have seen so far. So far we have been talking about running times that are O of n squared, of 2 to the n, of n factorial. But what is this all of a sudden? How does this function grow? Is this good? Is this bad? And I said in the beginning that it is going to be O of n log n. You don't see n log n here, right? So what we have here, this function, T of n equal to T of n over 2 plus O of n. This is called a recurrence. And recurrences arise when we analyze the running time of recursive algorithms. Because when we run a recursive algorithm, we want to describe the running time of the algorithm T of n. We are usually calling the function, the same function itself. So we will see the same function t, but on different parameters. Okay? So this is a recurrence. And when we deal with recursive algorithms, we are going to see these recurrences arising to describe the running time. And while this does not give us the sort of functions that we are used to seeing and give us an idea of how bad or good the algorithm is, there is a technique for taking this recurrence and writing it in terms of an explicit formula. So I can take this and I show that this, in fact, evaluates to O of n log n. But when we have a recurrence like this, before we are able to get the explicit formula for T of n, we also have to put a rule for the base case. Because look at this, T of n is 2 T of n over 2 plus O of n. Then I can say it is 2 of, this is T of n over 2. But what is T of n over 2? It is T2 times T of n over 4 plus O of n over 2. And I can keep repeating this exercise and getting all these copies. But where do I stop? Right? Where do I stop? So where I stop is exactly where the algorithm stops. How did we define merge sort? We define merge sort to stop when it gets to a list of size 1. So when it gets a list of size 1, all it does, it just returns, because it doesn't do any more work. So this is why we write that we have a base case here, and I have to define it, which is, in our case here, it's for a list of size 1. When the list of size 1, this algorithm does a constant amount of work, which is O of 1. Right? So when we write a recurrence, we have to write the recurrence formula, and we have to write a formula for the base case. The base case should not be a recurrence. It should be, again, a specific explicit formula for how long it takes the algorithm when we reach the simplest instance of the problem. So for merge sort, this is really what we get. This is the running time of merge sort in terms of the recurrence. The question again, how does this grow, and why is this O of n log n? And this is what we are going to talk about next.